No.
Hello, Mr. Ryan, right? Yeah. Hello, Mr. Eric, Mr. Ryan, right? Yeah. Okay, so what did we talk about last lessons? Like literally 2 days ago?
We talk about pigeonholes.
No,
yeah.
that's the one before that. What's the lesson? Remember? In what we talk about in Microsoft?
Oh, that one. Fence.
Yeah. Okay, it's okay. So
Ow.
we have n fences, okay, and then we have k colors, and we want to find out the number of ways to paint the fences with k colors. The only requirement is we can paint 3 walls with the same colors, okay, consecutively. Okay, so no 3 consecutive fences are painted with one single color. So when n equals 0, what's the answer? We're given no walls, no fences. When n is 0, okay, 0, yeah. This is special case, okay? We are given with n actually bigger or equal than 1, okay? When n equals 1, how many ways? If we only given one single wall, no, we have k colors. K, yeah, k.
K times K.
Yes. Why is it k times k if we have 2 walls only? Why is it k times k? Why is it k times k? Yeah, because look, first wall we have k colors. The second wall we have another k colors. The multiplication, k times k. Okay. So here comes the interesting part. If n is bigger or equal than 3, we talk about how do we achieve this problem.
4吧
Okay, so when n is bigger than 3, bigger or equal than 3, so how do we approach this problem? So we can look at this. For example, this is n, right? This is n's wall, the last wall. Okay, so there are 2 ways of painting the color, painting the last wall, last fence. Okay, so if it's different, okay, if it's different than n minus 1, for example, this is n minus 1. If it's different, then we have k choice. Am I right? Because look, we have k colors, and I'm telling you the last one is different than the previous one, so that we have k minus 1 colors. Okay, and then the number of ways to paint it n minus 1 fences is fn minus 1, right? Okay, we have this part. But if it's the same, if we painted the last fence with the same color as the second last, so we can't simply use fn minus 1 because this is n minus 1, right? This is n minus 2. If we simply use fn minus 1, then that will include the cases when the last 3 fences are painted with the same color. This is not right. This is incorrect. So how can we approach this problem? If these 2 are different colors, then we can paint the last wall with the same color as the previous one, right? So this is different. What's the answer? If the second last wall is painted with different color as the third last wall, so we have k minus 1 times fn minus 2, right? Okay, so the last wall painted with the same color as the second last, then this is the answer. And then we add it up together. So these are the equation. K minus 1 times fn minus 1 plus fn minus 2. Last lesson, we get this, right? This is the equation, dynamic programming equation. Now we can solve this using the top-down dynamic programming, using the recursion with the minimization, right? Define fn. If n equal 0, return 0. If n equal 1, return k. If n equal 2, return k times k, or k times k to the power of 2, okay? Otherwise, we return this one, and then we use the cache. This is top-down dynamic programming using recursion. Okay, so when k is 2, okay, one question, when k is 2, so this becomes 1, right? So what do we get? Fn equals Fn minus 1 plus Fn minus 2. So what's that? When k is 2, so what do we have?
Oh my god.
When k is 2,
Six.
fn equals
7.
fn minus 1 plus fn minus 2.
2.
What's this?
Fibonacci.
Fibonacci, but not quite, because Fibonacci number, the first two items is 0 and 1, but this is, the first two items is k and k times k, right? But if k minus 1, if k is 2, then this is quite similar to Fibonacci, right? So when we talk about the Fibonacci, we talk about the top-down dynamic programming, and we talk about the iterated approach, bottom-up, right? So we just have to, look, we just have to use two variables, right? We can calculate from f0, f1, f2, we can calculate bottom-up, right? Bottom-up approach. And as you see, fn only depends on fn minus 1 and fn minus 2. What does it mean? It means that if we want to calculate fn, we only require two previous values, right? So we can just iterate it using two variables, a and b. Let's write this. Define f and k. So yeah, these are the three base cases we put it here, right? So we can immediately return fn if it's less or equal than 2. We don't need to calculate because this is known. So ab equals, so the first two items, ab equals k and k times k. For I in range, we start with the third item to n inclusive, n plus 1, okay? ab equals b k minus 1 times a plus b, okay? And then return b. This is the iterative approach. So let's say if k equals 2, okay? So the first item is 2. The second item is 4, right? 2 times 2. The third item is the sum of the previous one, so which is 6. The next item is 10. The next item 16. The next item 26, right? 42, etc. So each item is the sum of its two previous sum, okay? AB equals B, this. How do we interpret this? So for example, AB, right? This is AB. Now we want to change it to B and then A plus B times K minus 1. Okay, K minus 1. So look, yeah? So A becomes B. B becomes A plus B times K minus 1. So for example, this is A, this is B. So if we move it, shift it, so the next iteration, this window of size 2, shift it to this position. So this becomes A, right? This becomes A. So A becomes the previous B. B becomes the previous A plus B. Okay? So this is how we interpret it. Do you understand? Yeah?
Yeah.
So the time complexity for this one is O. The time complexity, O(n). Okay. The space complexity is O.
1.
1, yes.
Yes!
It's better than this one because this one we're using a cache. The space complexity is O(n). Okay. The time complexity is O(n). This is better because we're only using two variables iterated, right? Why this is more memory efficient than this one? Look, when we want to calculate this value, we only require these two values, right? We don't need anything before that. We don't need to store anything before that. We just need the sum of the previous two, right? All right, and times k minus 1. All right, yeah. Does it make sense? This is the same as Fibonacci number. Only difference is the first two items are different. For the Fibonacci number, the first two items is 0 and 1, and the k is 2. Okay, but in this case, it's the first two items is 2 and 4. Actually the first two items is k and k times k, and there's a k minus 1. We need to multiply it. The principle is the same. Okay, so this is called bottom-up dynamic programming. We want to calculate fn, right? So we start with f0, f1, f2, f3. Each value, each fn depends on the previous two values. It's more efficient because we are not recalculating, right? Each value is calculated only once. Am I right? Yeah?
Mm-hmm.
Dynamic programming. The one key thing about dynamic programming is one advantage of dynamic programming is that we remember the intermediate results, so we don't need to calculate these fn over and over again, so it's more efficient. Okay, that's it for today. Bye bye.
Bye.
Bye bye.